Yeah, a very similar idea is the discrete wavelet transformation. So the only difference is that we represent the time series now as a linear combination of wavelet functions, typically so-called Haar wavelets, which you see here. Yeah, and similar to the Fourier approach, also the wavelet transformation computes n components. Yeah? And the key here is that the more stationary the time series is, the better is the approximation with fewer components. Yeah, so the same trick, but only if the assumption holds that the thing is stationary. Yeah, so it doesn't make big amplitude hops, so to say. Yeah, distance on wavelet transformation components are also a lower bound of the Euclidean distance, and also to a lower bound of dynamic time warping distance on the original time series, similar to the Fourier transformation. The only downside, so to say, is beside this assumption that some or the parts of the time series should be stationary, is that the original time series are restricted to be of length 2 to the power of some value. So Zweierpotenz. Why that is, we'll see right in a minute when we have a look at how the things are computed. So how are the discrete wavelet transformation is computed? Well, for each odd index I, we compute the mean of pairs xi and xi plus 1. Yeah, and so we compute the mean and the offset, which is computed by the left one, xi, minus the mean. Yeah, and we repeat this for the means until there is only one mean value, which is the mean of the original time series, of the entire original time series is left. Yeah, and that's why we need a Zweierpotenz here, because we just in the first step we just sum up, so to say, or approximate pairs of values. Yeah, and we do that consecutively until we have only one mean computed for the entire time series. Yeah. So here's an example if you cannot really capture that. So the original time series is 9, 7, 3, 5, 6, 10, 2, 6. Yeah. So in the first step, we compute for all pairs the mean and the offset. The mean of 9 and 7 is, so for odd index 1 and 2, so 9 and 7, the mean is 8, and the offset is the left one minus the mean, so 9 minus 8 is 1. Yeah? So for the first pair we compute mean 8, offset 1. For the second pair we compute the mean of 3 and 5 is 4, and 3 minus 4 is minus 1. That is the offset for those for this pair. The same here, 6 and 8, so the mean is 6 and 10, sorry, the mean is 8, and 6 minus 8 is minus 2. And here we have 2 and 6, so the mean is 4, and the offset is 2 minus 4 is minus 2. Okay, and here we go. So we have 6 now, 8 and 4, and we can again compute, since we still have 4 means, we have to do that until we have only one mean. So we do the same procedure with the means. So we compute the mean of the means here. The mean of 8 and 4 in the second step is 6, and the offset is 8 minus 6, which is 2. No? And the same holds true here. 8, 4 is 6, and 8 minus 6 is 2. And we're still not done, so we still have 2 means left. So we compute the mean of those means here, which is 6, and the offset is 6 minus 6, which is 0. And now we just have to keep the last mean, this 6 here, and the offsets in reverse order of computation. So we keep the 6 here, this is the last mean, and the offset, which is 0. And then we have to keep 2 and 2 for this one here, and we have to keep 1, minus 2, and minus 2 for those offsets here. And interestingly, we can compute from this sequence here, we compute the original sequence just by doing the computation we just did in a reverse order. We just need this mean, which is this one here, the first one. This is the mean of the whole time series, so to say. and we need the offsets. That's the only thing we need to reverse this transformation. Yeah? So dft will transform this original time series into this new representation, which is the mean and the offsets. And you see here again that it's of course this of the same length. Yeah, so we had 1, 2, 3, 4, 5, 6, 7, 8. So a time series of length 8 is transposed or transformed into a representation of 8 values. The first one is the mean, and the remaining 7 ones are the offsets we computed during computing the mean. So that is the idea of the discrete wavelet transformation. And the point again is if the time series are stationary, a lot of those things here are similar, and then we can just again erase the last offsets here, because most of them are 0, and then we don't lose too many information down here. Yeah, so that is the basic idea. And you see that here the 0 here comes from two means which are obviously the same. Yeah, so always if there is a 0, it's a kind of stationary thing, so to say. Yeah, and if it's down here, it means that the offset of pairs here are more or less 0, so we can just get rid of them. So basically the same idea like Fourier transformation. Yeah, we transform a time series of length n into a representation of length n, and then just keep only a subset of those representation values, like PCA, the same idea of PCA. No? By the way, PCA, we can also use singular value decompositions, which uses eigenwaves. We call them eigenwaves in that case, instead of sinus and cosine or wavelets as base functions. We don't go into details here. Just the properties. It minimizes the quadratic approximation error, like PCA and SVD on high-dimensional data. Okay, the semantics of the components of SVD actually depends on the real data. So DFT and DWT, sorry, the semantics are quite clear or fixed, because in Fourier we have sinus cosine base functions, in wavelets we have those constant base functions, and here with SVD it's a data-driven semantics. Yeah? So the components we have, which we call the eigenwaves here, you see here, those are the eigenwaves computed from those time series here, or from the red one here, is data-driven actually. Yeah? And in text mining and information retrieval, SVD as a feature extraction technique is also known as latent semantic indexing. You may have already heard about latent semantic indexing. So if people talk about latent semantic indexing, don't get confused. They're just talking about SVD as a feature extraction technique. Yeah, so don't get impressed by people talking about latent semantic indexing. You know about that. Yeah, then piecewise aggregate approximation, which is the next one, PAA. So it transforms time series into a sequence of box functions, as you see here. Yeah. So each box has the same length and approximates the interval by the mean of the corresponding values. Yeah. Within this interval. So you see here that, for example, for this interval here, you just take the mean, yeah, and for the next interval you take the mean, and for the next interval you take the mean. So this blue representation, of course, is not the perfect. It's the representation of the red one, but shifted down here along the amplitude spectrum, obviously. Yeah. Okay. So it's a kind of downsampling, but instead of just arbitrary sampling, we're using means as a representative value, yeah, and not just the middle value, so to say. Yeah, properties. There's also a lower bounding property to Euclidean distance and dynamic time warping. Time series may have arbitrary length now, so it's a little bit similar to wavelet, but a little bit more flexible, because we now have we can have time series of arbitrary length. And there is PAA is especially good if there are intervals, repeated intervals with the same length, each having values with a similar amplitude, obviously, because then the mean value is really a representative. So if you have within those intervals a very high spectrum of amplitude values, then of course the mean value is not very good. Yes, but if you have a lot of equally length intervals where the time series is quite stationary, then this of course is a very good approach. But obviously this is again a very strict assumption on the data. Yeah? But anyway, yeah. So and now just easing or make it a little bit easier about this very hard assumption of these fixed size intervals where the signal of the time series is quite stationary. We use adaptive piecewise constant approximations, APCA, an extension to PAA. So the time series may have time intervals with a small amount of details, small amplitudes, and the intervals with a large amount of details, with a large amplitude. And in that case, of course, PAA cannot account for those different amounts of details. Yeah? So we have small amplitude, small amount of details with large amount of details, and PAA cannot capture that. And APCA uses also box functions, but now and boxes, not boxers, but boxes. But now not of fixed length, but of arbitrary or variable length. Yeah, so each segment now, of course, now is a little bit more complex, because we now need 2 parameters to represent each segment. So in this case, we only need the mean value, because the length is always fixed and the beginning and the start is always fixed. So here we now need not only the mean, but also the length of the segment. Yeah, so we need to know that this segment is just from here to here, and this segment here is from here to here, much longer, and so on and so on. And of course we need the mean. Yeah, so APCA is a little more adaptive, much more adaptive, but it has the downside that we store the representation is double size. Yeah. Okay. Yeah, and finally we have these piecewise linear approximations, another extension to PAA, where we now not only store the mean, but we store actually line segments. Yeah, so we approximate in each interval, we approximate the time series by say not the regression line, well the interpolation line, so to say. Yeah. So we need for each line segment, we need the length again, because the length of the intervals can be variable, as you see here, and then we store the amplitude value at start and the amplitude value at the end. That's all we need to restore a line segment within this interval. Yeah. So now 2 consecutive segments need not to be connected, which can be sometimes a little bit nasty for other pre-processing things and stuff like that. So just keep that in mind. And of course, PLA yields a richer approximation of the intervals, but again requires one more parameter. Yeah, so we trade accuracy against compactness, and of course the accuracy of the approximation depends on the length of the segments. There should be the length of the segments, of course.